start with problem one. Problem one is very standard. It's we have gone through this many times. But consider a solid sphere with uniform charge density. So solid sphere, radius capital R, and charge density is rho. It's uniform. So charge density is uniform. Find the electric field inside and outside of the sphere. Okay, find the electric field inside the sphere and outside of the sphere. So we start with inside the sphere. Okay, the electric field inside the sphere. Meaning little r is less than capital R, right? This you should be able to do quick. Who can suggest what's the approach? What should we do? Yes?
Gauss's law.
Gauss's law.
Yeah.
So draw a Gaussian surface and apply Gauss's law. What kind of surface?
Sphere.
A sphere, not a cube, not a cylinder, right? We have spherical symmetry. So we got, here's our Gaussian sphere, or Gaussian surface, radius little r, like Gauss's law. Now, by symmetry, in what direction is the electric field? By symmetry, what's the direction of the electric field? Assuming the charge density is positive. Outward, meaning radially outward. Radially outward. In what direction is the area vector? Radially outward also. So they're parallel to each other. So E dot dA becomes E dA. And if R is constant, little r, if we static on the surface area of that sphere, E is constant. So we can pull it out of the integral. So it becomes EA. What's A? It becomes EA to the left side. And what is A? The surface area of the sphere. How much is it? I think that would be the volume. That'd be volume. 4 pi r squared, yes. Little r or capital R? Little r, it's the Gaussian surface. So, little r, so little r squared. Okay, so now, Q enclosed, it's a uniform charge density. So how much charge is within this Gaussian surface? How do I get? Rho times V. Yeah. And what is V? Yeah, what's V? What's the volume? Four spheres. 4/13 pi r. It has to be cubed, it's volume. So now notice the 4 pi and the 4 pi, the r squared cancels with one of these. So we got the electric field to be rho over 3 epsilon naught. Oh, let me take the vector out first. And times r, right? In what direction is E now? So let's make it into a vector. So put it with a different color. We already concluded the direction before even doing the problem. What's the direction? Radially outward. How do we represent that with a unit vector? R hat. Now R times R hat is what? R vector. So now, so therefore, E equals rho over 3 epsilon naught R vector. This is inside, right? Next one is, what's the electric field outside? Have to draw another Gaussian surface, right? And what should be how should the Gaussian surface look like? A big sphere, bigger than the shape itself. So it would look like this, right? There's another Gaussian surface. It would look, sorry, it's not so spherical, but it's supposed to be. The yellow sphere now, right? So we do E dot dA. Okay, so same drill. What is E dot dA? What does it become?
EA.
EA, and so that's E times what?
4 pi r squared.
4 pi little r squared, right? Little r squared. Epsilon. So now QA closed. It's rho times 4/3 pi what? Pi r cubed, yeah. Little r or capital R? Capital Y.
Because the charge enclosed.
Yes, because is there charge enclosed out here?
No.
So the charge goes up to here. So be careful when you put the R. So in here, it would be capital R. So R cubed. So we get 4 pi now to cancel. So we get the electric field. Rho R cubed over 3 epsilon naught 1 over R squared, right? R squared. Are you surprised that the electric field drops as 1 over R squared? Or not surprised? You should not be surprised. Why not? Because
It's moving that away from the surface of over r squared.
So the sphere, a uniformly charged sphere is like a point charge once you're outside. Right? We mentioned this. You're outside of it, behave spherical shells or solid spheres. Behave like a point charge. So when you put the vector back, we already concluded the direction of this. This is outside. Problem two is a solid cylinder, infinitely long cylinder. There is a and the charge density is rho. In the cylinder, the charge density is rho. This infinitely long cylinder, this is the cross section here. Otherwise, the cylinder would extend upward to infinity and downward to infinity. Question, the electric field, in what direction is it going to be? Radially outward also, right? In the sense of cylindrical coordinates. Yeah. So it's not parallel to the cylinder, but rather perpendicular to it from all directions. So we want to find the electric field. By the way, this is from the same example. So problem 2. And the electric field inside the cylinder and outside of it. So inside it, that's R less than capital R. This is the axis of the cylinder. So how should our Gaussian surface look like? Cylinder. Inside the cylinder, right? So that Gaussian surface should look like this. Cylinder should have the length L, right? Or height H. And the radius of our cylinder is little r. The radius of our cylinder is little r. So we, again, Gauss law, E dot dA. Closed surface integral. We conclude closed surface here is a cylinder, right? It's not a sphere, it's a cylinder. Cylinder has to be closed. It has a top, a bottom, and a middle part. In what direction is the area pointing at the top? To the top. In what direction is the field? Also, or radially out, yeah, it's radially outward. So the area points this way, but the field is always radially outward. So what angle do they make? 90. What's the dot product?
0.
0. Now on the bottom, the area points down, but the field is still perpendicular to it. So what's the dot product there?
0.
Another 0. The only one that survives is the middle. The middle, the area points radially outward, and the field also points radially outward. So what's the dot product?
Yeah.
EA. E dot dA becomes EA, right? Okay, good. So it becomes EA. So E times the area in the middle. What's the area in the middle?
2 pi RL.
2 pi RL. Good. Now this, we need to figure out the charge enclosed within our Gaussian surface, right? What's the charge there? What's enclosed? It would be rho times the volume. What's the volume of a cylinder of radius R and height L? Should remember it.
2 pi r times r?
2 pi R.
Oh, wait,
That's
it's
the
not
area.
It's the cube or squared.
It should be length cubed, but so it should have total cubic meters, right? If we were in SI units. So the cross-sectional area times the height. So the cross-sectional area is pi r squared times L. That's the volume of the cylinder. That should be remembered. So the length cancels, pi cancels, one of the r's cancels, and we get E equal to R over 2 epsilon naught. And we said the field is in what direction? In the outward, so we put R hat. And what is R times R hat? R vector. Outside now. We need to find the field outside. For R greater than capital R. How does our surface look like now? A bigger cylinder that would encompass this way. Here it is. I'll draw it here. Right? For a change, let's call it H. And this is R, right? So E dot dA, the left side, anything changes? On this side, what do we get? Would it be, would it look like this?
Or, yeah, H instead of the L.
Or instead of, I'm calling it H instead of, yeah, otherwise it would be the same, right? Yeah. E times 2 pi R H. On the right side, you enclose over epsilon naught, you get rho times the volume. Well, what's the volume? So it should be
Pi r squared H.
pi r squared H. When you say R, which R?
Capital R.
Capital R, right?
That's where the charges are enclosed.
Because, yeah, when little r is beyond capital R, there is nothing in there. There is no charge. That's it. So now, the pi why are we not surprised that it depends as 1 over R? When we're outside, why does it drop as 1 over R? For a sphere, we said 1 over R squared, right? Because it's like a point charge. How does the cylinder look like when you're outside of it? Like an infinite line charge. Like an infinite line charge. So now, the next one is problem 3.
Mr. Professor, is there any practice problems I didn't get to look at where like we don't have when we have non-uniform charge density?
Yeah, practice. In the practice exams, you need to have no points. So,
Will we be able to go over one?
sure, we can do one. Let me finish this one and then we can do one. Yes.
So for the 2 pi RL, that's our area for the
Middle part, yeah.
Middle,
Yes,
right?
exactly.
What difference would it make it instead of our cylinder being vertical, it was like horizontal?
That's a good question. It will not have the same symmetry. In
Oh,
that
you're right,
case,
yeah.
the middle part will no longer be parallel to the field. Does that make sense?
Yeah.
Yeah, when you ask such questions, it means you're getting it. That's good. Yeah. So that's what's important. Problem 3. Problem 3. So this exam, you know this. I asked them. Problem 1 was to set up the seed. Problems 1 and 2 were to set up the seed for problem 3 because they need these results. So here's problem 3. Problem 3 looks like this. We have an infinitely long cylinder. Here it is. That's the infinitely long cylinder. The radius is capital R. Okay. It's infinitely long. This is the axis of the cylinder. And, well, if we just leave it as is, the charge density, of course, is rho. If we leave it as is, we'll just get the same results we just got. But we don't want that. We want to modify. So this problem says this: somebody comes in and scoops out a spherical part of it. So somebody reaches in and scoops out this much. And the radius here is R over 2. So here you have a hole. It's empty. Okay. It's empty inside there. The question is, what's the electric field inside here? What's the electric field right here within the cylinder but outside of this cavity? And then what's the electric field outside both the cavity and the cylinder? What's the electric field out there? Right here. So what's the electric field inside the cavity? What's the electric field right here? And what's the electric field right here? And the idea is this: when you have a cavity, it means how much charge do you have? 0. How do I, what's a different way of getting 0 charge? That's right. So if this one has, the cylinder is still solid with rho, somebody grabs a sphere with the same density but negative rho, and then pushes it on here. And now you will have a net charge of 0. So the total electric field will be due to the whole cylinder plus the electric field due to the sphere, due to the solid sphere. So inside, so for R between 0 and R over 2, between 0 and R over 2, right? We're inside the cap. The electric field is going to be this. What's the electric field due to an infinite cylinder when you're inside the cylinder? Electric field. Yeah, we have the result. It's there. Okay. So rho over two epsilon naught vector r. So it'd be rho over two epsilon naught vector r plus, what's the electric field inside a sphere? Inside the sphere. We shouldn't be looking here. It's somewhere else. We found it. All right. Right here, inside the sphere. Sure. That's the electric field inside the sphere. But the charge density though is negative. So I will put minus. Rho over epsilon naught r. So, see, a really difficult problem or intimidating looking problem becomes really easy. So we get, subtract them, we get a half minus a third becomes a sixth. We get rho over 6 epsilon naught. How about here? So now we're outside of the sphere, but still inside the cylinder. Somewhere outside the sphere, inside the cylinder. So we get E equals. Inside the cylinder, we're still inside it, right? So this equation, this formula still applies. We get rho. So R minus. But now we're outside of the sphere. What's the electric field outside of the sphere? Out there, right? Rho down. On 3 epsilon naught. Oh. This would be technically not correct. There's one little. It is, yes. The radius of the sphere, given earlier, was capital R. But the radius of our scoop sphere is how much? It's R over 2. So here I need R over 2. This should be R over 2. Otherwise, that's fine. That's it. I won't simplify this. I'll just leave it like that. If you have a question, please let me.
It's kind of a general question, but like, is it safe to assume that when you're solving these kinds of problems, you get the same equation at the end just with like different variables? So like you can get different all or like radius, different areas length, but it's like all the same. Kind of?
Similar approach. Yeah, like
Just-
whenever you have symmetry, you basically have Gauss's law. But not necessarily like the same result at the end.
So the bottom one was outside of the sphere, inside of the cylinder, and
Mhm.
the top one was just inside the sphere.
Inside both of them, yeah.
Inside.
Yeah. And then the last one, you're outside of all of them. For this last part. So R greater than capital R. What's the electric field outside of the cylinder? That's right. That's what we draw it first. And then for the bigger sphere, when you're outside, the scoop, when you're outside of it, it's still this. So, and
Could you break down what we're subtracting what from? Is it always, outside minus or inside minus outside?
No, this is the electric field of the sphere that's negatively charged, and this is the solid cylinder.
Oh, okay.
Yeah. Remember, the problem was, we scooped out something, so we actually have a cavity here.
Oh, okay.
But we changed it into a problem that we can do, because that problem, if you try to do it like that with a cavity here, you don't have the symmetry.
So it's that minus the cavity.
Most of the time when you have a cavity, do you use the approach of like, you have something positive and
Yes,
something?
yeah. That would be the, especially if you wanna find the electric field inside.